going first, and then Barry.
Sounds good. Thanks, Allison. Give me just a moment. I'll share my screen. Okay, that's showing up okay?
Yes, it is.
All
Thank
right.
you.
Thank you so much. Okay, hi, I'm Bob Roginski with Eigenvector Research, and I'll be kicking things off today talking about considerations, basically things you might want to think about when deploying your model or models in your application, and that will segue into Barry talking about how do we keep our models up to date with some things to think about on model maintenance. So you've built your model or your models. Now what do you do? And as it turns out that there's many types of objectives for models, and when I talk about models, I'm talking about in general a mapping that's being made from multivariate measurements to some type of outputs that are desirable for you in terms of monitoring or controlling your process. In this instance, we're going to focus on deploying models that we are looking to get real time or near real time, or even samples that are pulled into a lab and measured, let's say spectroscopically, to take the place of a longer laboratory test or laboratory test that is not particularly safe to operate. With our model or models, that we have built on a carefully constructed calibration set, we're going to apply those models to new measurements or observations to produce results that are meaningful to us, or perhaps just monitor. Again, that ties back into what is your overall objective for the model that you have constructed. There's many types of models that can be deployed. Regression is probably the most common, where you're going to make a transformation on your data, and from that predict concentrations or properties or something of that sort. Another widely used category is classification. I perform a measurement on my sample. I want to know, is it good or is it bad? Or if it's a product that I can make multiple grades, which grade am I making at that point in time? Or am I perhaps in some kind of transition between grades? Data reduction, and this can be particularly helpful for statistical process control, where we're now going to look at a lower dimensionality representation. An example of that would be PCA. And what I mean by that is, if I collect a spectrum of a sample and my acquisition parameters are such that there's 1,000 data points per sample, it gets difficult to envision things in 1,000 space. But if we can represent our measurements in a lower number of dimensions, 1, 2, 3, 4, 5, something of that sort, that really helps us to glean information that will help guide us in our decision making. And then you can have a model construct that is a combination. For example, a hierarchical model. It may be the case where, if you're trying to build a classification model and there's many different classes or groups, doing it all in one fell swoop might be too challenging for your classification algorithms. In that case, it's often helpful then to break the problem up into chunks. So initially try to classify between two or three separate groups, each group containing two or more classes. And then you break that down further with each of those legs having their own classification models. Or you can have a classification model combined with a regression model. The example that I mentioned earlier, where if I have a product that is made in several different grades, I may have regression models that are optimized for each grade. So if I can have a single model construct that will first determine which grade I am making, and then apply the appropriate regression model. And that's handy because it doesn't not require any further intervention in the model application process. The scenarios are highly varied and depend on the industry, so food, pharmaceutical, petrochem, semiconductor. That the needs are varied across all of those different industries. And your implementation is also going to depend upon the process that you're actually monitoring within that industry. Your implementation is likely going to depend upon the location and infrastructure. If this is an online analyzer and it's producing results continuously, they need to go somewhere. And that's that last bullet point, fate of the outputs. And depending upon how information is gathered and stored at the plant, that's going to that's going to have a bearing on how you implement your model application. What kind of communication protocols are there within that plant for the handling of data? One way you can look at this, as far as going back to that early slide, now I have my model. What do I do? There's 4 questions here that you can focus on and help you to decide how to get your model successfully deployed. First and foremost, where does the data come from? And this is the data, these are the measurements that we want to apply our model or models to. Second, once that data is generated, how do we trigger the application of the models? What's going on behind the scenes? What's the man behind the curtain doing to be able to apply those models and then get results? Different models, different model types are going to have different types of outputs. You may or may not want all of the outputs from a given model type, but at some point you need to make the determination which outputs are required. And then finally, once those outputs are generated from the model or models, where do they go? Okay. So what we're going to step through here is a number of scenarios ranging from very simple, you might not even think of it in the sense of being a model deployment application, but if you've done, if you have some experience in a industrial lab building methods, this is where we're starting. This is the easiest scenario. And then we're going to step through and add little nuances to each succeeding scenario, and just to give you some ideas of what you should think about on how you would handle them. So the first example here, we're going to talk about having a lab spectrometer, and we're going to apply a regression model. And this is this could be something as simple as I have a benchtop mid-IR or Raman instrument. I have a nice isolated band in the spectrum. I do a little baseline corrected area measurement on that band, and there is a slope and an offset that I apply to that area to get a property of interest. And then my results, I'm going to want to go that into a report file, a PDF or a CSV. Well, a lot of this is already covered by instrument software to varying degrees, okay? That's where you set up your method. You set up your acquisition parameters, and then you can define your area measurement. A lot of instrument companies they've implemented some level of more advanced models, so perhaps MLR, where you might be looking at multiple peak areas, or PCR or PLS. But the idea here is that everything is being handled by the instrument software. So the user will initiate an acquisition, and then once the acquisition is completed, then the instrument software is processing it accordingly, and then it goes to a report file, and you're done. So the thing to highlight here, this is a single software platform, pretty simple to implement. But where might you be limited? It may not be possible to use more complex models. At this point, you're limited to what is available to you from that instrument software. All right, next step. Same spectrometer, same regression model, but now we're going to take our results and port them to a LIMS system. And here we're looking at the same instrument software governing the acquisition. And then now, once that acquisition is completed and the model is applied to the data, now that has to find its way to the LIMS system. Your instrument software may have direct hooks, or maybe this is done passively, where the file, the reports file might be saved to a particular location, either on the computer itself that's doing the acquisition, or a computer on the network, and then the LIMS system will swoop in and grab those results, parse that file, and then add them to the database. But here we're looking at there is a step that is required to get those results outside of I'll call it the instrument software infrastructure, and get it to another place. Oh, I call this mostly a single software platform because you now have this secondary system, a LIMS system, that you want your results to ultimately reside in. And you need to figure out a way to get those results into that LIMS system. So the questions, second bullet point there, can the instrument software produce an output that's suitable for the LIMS system? Hopefully. And then, a little nudge here, be sure to make friends with your LIMS administrator, because this is the person that's responsible for the integrity of that system, and you're probably going to need to interface with that person pretty closely to ensure success for your model deployment. Okay, scenario 3. The second bullet point here is where things are differing. And now we're going to employ an advanced regression model. And what I mean by that is a regression model, a model type that is not available from the instrument software as it is currently constructed. The beginning is the same. We initiate the acquisition. And then after the acquisition is completed, then we need to process that data acquisition. And that's going to be with software outside of the instrument software boundary there. And I show two lines there. The solid line represents the instrument software having what I'll call direct hooks into that the software which is outside that we can actually apply the model to it. And by direct hooks, the software, the instrument software might have something akin to a direct behind the scenes sending and retrieving of the data and the results from the instrument software to the process acquisition software. Or the instrument software might have a scripting language built in where then you can communicate with the software that applies the model to your data. The dashed line, you can think of that as there's not a direct connection, but the application of the model will take place regardless. And an example of that would be after the instrument software does a measurement and stores it in a folder somewhere on that computer or somewhere on the network, the software that applies the model to the data might be watching over that folder for new files to show up in that folder, and that'll trigger an automatic application of the model to that data. Or the software that processes the acquisition might be set on a timer. You can imagine where at a plant where acquisitions on samples take place at set times throughout a day. And then this software will monitor a folder at those set times and look for whatever files have been dropped. Okay, so at that point, you have applied the model or models to your data. Now, if you have direct communication from the instrument software to the secondary software, well, the results can be sent back to the instrument software, and then from the instrument software sent to the LIMS. Or you can bypass the instrument software and then trigger the process acquisition software to send the results directly to the LIMS by directive of the instrument software. Or the dash line, again, things are being done without guidance from the instrument software. So the process acquisition software will have the ability to process the acquisition by applying the models to the data and then send them directly to the LIMS. And that's summarized here. The acquisition is processed by a separate application. There may be direct hooks or scripting. And then depending upon what is the linkage between the instrument software and the separate application, you have different means of getting your results ultimately into the LIMS. Okay. Taking this up in a little bit further in terms of complexity. Now we're going to talk about separate lab spectrometers. So one, you might have a mid-IR coupled with a Raman, and you're going to run the same sample on both, and you're going to combine the data and use what's called a multi-block or data fusion model to apply to that conjoined data. So now you have two distinct instruments, each of which has their own acquisition software. And then the results from each of those will be combined and processed by the outside software that applies the model to the data. And that software will take care of combining the data in the appropriate order and then applying whatever scaling needs to be done as was done in the model building process. And then from there, we would, as in the previous slide, depending upon what kind of interaction we would have available with the LIMS system, the multi-block model would be applied to that combined data and the results forwarded appropriately. Now we're graduating from the lab and putting a system out into the plant. We have a process spectrometer, and running that is process software, and the little emoji here is meant to imply that that data is being collected in a continuous fashion, and you have a known cycle for this process measurement. Each cycle, the data will be handled by the outside application, the application which will apply the model or models to your data. And then after that, it's possibly sent back to the process software or sent directly from the external software to the likes of a distributive, a DCS, or a data historian to be able to be used at the plant level. And this is where each DCS or data historian, the considerations there are what types of communication are available, and are the softwares that you have in place, both the process software for the spectrometer and then also for applying the models to your data, how well do they fit in? So this scenario shown here would be where the process software gets the results back from the model application software and then sends it to the DCS or data historian. And then dash lines would be, and that's where the lines of communication are not as direct, and you may have to put a little bit of customization in to be able to get to your ultimate endpoint of getting the results into your DCS or data historian. Next scenario, we'll consider a process spectrometer with a multiplexer. Optical multiplexer means that with a single spectrometer, we can monitor many different points in a process or a plant. And an example of a cycle would be that for each cycle, the spectrometer is going to do measurements across each of those sampling points. Each of those sampling points are going to have one or more models associated with that sampling point. And that's designated here under process cycle, have the I equals 1 to n. N is the number of sampling points that you have in your system. As you can see now, this starts to get to be a bit of this could be a little bit of a bookkeeping challenge, keeping track of for which sampling point, which models need to be applied, and then for each of those models, which outputs do we want from those models, and then everything cleanly end up in the DCS or data historian. Last scenario would be multiple process spectrometers, along with, let's say, multiple sensor data. We can oftentimes build a multi-block or data fusion model. You saw earlier where we combined measurements made from 2 different spectrometers, and there's no reason that we can't add on, let's say, univariate sensor data that we deem appropriate, such as temperature, pressure, level, flow rate, pH, introduce those measurements into the mix. So a couple of process spectrometers, and that last graphic there, what I'm trying to imply is that I've got 3 univariate measurements that I will take a snapshot in time and get the values from each of those 3 sensors, combine those with each of the spectroscopic measurements, and that's going to be the input to my model or models. This, of course, is an increase in complexity. Now you have to get data from different sources and combine them properly. You may have timing issues. If I were to replace, let's say, one of those spectrometers, which can have cycle times, let's throw out there from 10 seconds to maybe a couple of minutes. If I replace one of those with an NMR spectrometer, well, the NMR spectrometer might require successful measurements integration times that are quite a bit longer. Well, that means that the other faster measurement, I'm doing many more of those. So how do I handle that? Do I average them, or do I just take the measurement at the beginning of the NMR cycle from the spectroscopic? But those are things that you can work out in development, and then determine what's the best way to build that model and then deploy it. PAT software can greatly simplify model implementation, especially in the last few scenarios there, in terms of the data collection from all of your instruments, and perhaps from a data historian. And in some cases, the PAT software can also be responsible for the data acquisition itself. It will help you with your model bookkeeping. Again, keep in mind the scenario where you have multiple models per measurement point. It's going to be very helpful for you to be able to get that done. And then the PAT software will have the necessary communications to tie into your infrastructure, whether it be in a lab scenario such as a LIMS system, or in the plant with the different types of protocols that are in use out there. A quick note about homegrown solutions. And homegrown solutions, what I mean is that you have someone on your implementation team. Let's say you're part of a PAT group, and you have an individual that is an incredible Python coder, and certainly you can do these things and especially show feasibility with homegrown solutions. Part of the issue, at least from what we've seen over the years, is that particular solution going to be scalable? But even more of a concern is it sustainable? Is it supportable over the longer term? If that individual in your group who put all that together moves on and you encounter needs to make changes down the road, that that can really gum up the works. A few closing comments. Each industry is going to have, at the very least, some guidances, and on the other end, you have you can have regulations. There's regulatory needs that need to be met. For example, pharma, you have 21 CFR 11 considerations, or EU GMP Annex 11 considerations. Guidances, example of that might be in the petrochemical industry. There's a slew of ASTM guidances for building models. These are things that you need to be conversant with. What are the needs of your particular industry, and how they may, and how you're going to meet those needs. The good thing is that your vendors have done a lot of the legwork for you, and and oftentimes will provide for you essentially a plug and play solution. Understand the flow. I guess that's the take home message that I want you to get from this, is that model deployment, it's great that you've been able to build a model on your calibration data. Now you want to put it into play and understand what individual components are needed to make that deployment successful, and what each of those components can do and what they can't do, and then how do you bridge those gaps. And with that, I'd like to pass this on to Barry, who's going to convince us that models don't necessarily work forever. So thank you for your time and attention.
Thanks, Bob. As you listeners out there might imagine, we've run into all these scenarios over the last 30 years here. And what's sort of interesting is how when you start one of these, some of the stakeholders don't know their own landscape very well. And it takes a while to figure out how all the parts that they have available are going to fit together. So I'll just leave it with that. And let me see. I will share my screen and get going. Okay, why model maintenance? Well, there are a lot of things that can cause calibration models to become invalid and produce poor predictions or classifications. Samples can move to a range outside the original calibration. New variation can get introduced into the sample, or you can get a change in the sample matrix that causes the relationship between the analyte and the measurement to change. And then, of course, there's the changes in the hardware themselves. So there's a lot of things that can happen that makes your models start producing results that aren't right on. So the first thing, though, that I want to say here is before your model goes online, it's a really great idea to develop a plan for maintenance. Assume that upgraded or new calibration models will eventually be required. There are a few very long-lived models out there. There's an awful lot of them that last a whole lot less time. And because they're dealing with input streams that are constantly changing, things like that. In any case, plan for your model to eventually need to be updated. have a plan for how to detect the problem and track down what the source of it is and put it in your budget. Also, we highly recommend the measurement of standard samples if possible, and we know that that's not always possible in a lot of scenarios, but plan for registration and amplitude shifts in your instrument. Characterize instruments in the ranges important to the model. And 30 years ago, we thought this was eventually all going to go away, that there was not going to be a need for instrument standardization. And it turns out there still seems to be that. So plan on that happening. So the first thing is, how do you detect model data mismatch and performance degradation? Well, you can use things like PCA models with spectra residuals, Q or similar, and sample distance from the center, T squared or similar. You can, of course, monitor the prediction accuracy via the primary reference method. So in that case, it's really unlikely that a change wouldn't be detected by the diagnostics, but it's possible. Also, you might implement a risk-based approach there. We could talk about that a little more later. In general, detecting that something has gone wrong is way easier than determining what has gone wrong. If you're not monitoring via the reference method, then the job is even harder. And why aren't you? I think in most systems, it's a really good idea to be monitoring occasionally, checking via the reference method that your predictions are still good. Here's the general idea of a PCA model where we have our data cloud as the red points, and we have a couple of interesting points. This is a sample with high Q that's a long way off the plane, off the subspace that the rest of the data is in. Here's a high T squared sample that is a long way from the center of the data. So those are two diagnostics that we look at a lot when we're monitoring models. But how do you set limits on those diagnostics? It's often helpful to think in terms of failure modes. For processes, what are the undesirable states? I mean, what could go wrong? Use these undesirable states as rational guides to setting limits on Q and T squareds. The main consideration, though, of course, is impact on the prediction error. Is you want to keep the prediction error on the analytes that you're trying to monitor or properties you're monitor to within a certain range. So you can use extreme values or summaries of what might go wrong. But the basic idea is choose an acceptable level of impact on the prediction error and then determine what are the corresponding values for Q and T squared that you are at when you hit that. So this is a little different idea than just monitoring a statistical confidence level. What you really want to get to is some engineering level on these, is how bad do your diagnostics have to be before it actually impacts your prediction error. All right, well, how do you detect model data mismatch? This is a little synthetic example, semi-synthetic, to illustrate change detection issues. The model I'm using here is from near-infrared measurement of isooctane in the presence of interferences. But if you're going along and things are nominal, your data might look like this. And here your test samples are the red diamonds and your calibration data is the gray circles. So if things are going well, here in your Q residual versus T squared plot, you'd have both your calibration and your test data. We generally expect, especially if you've had fairly small calibration sets, that you do occasionally get things outside the 99% limit here, Generally, that doesn't impact things if they're not too far over the line. And then here's a scores plot that we might get in that same example. But if you are still using the reference method, we can check these things. We can check whether the predictions are also in agreement with the actual values and what the residuals on those are. And I want to point out, so these two plots you can only make if you have the reference method available. The two top ones you get all the time. So if you get some out of range samples, that's going to look like this in your Q versus T squared. Here, higher T squared values, scores plots, they wander off. And here, though, typically, if they're just out of range, your model typically still gets pretty good predictions. And again, that plot you only get if you've got the reference method available. If you have a new interferent, it might look like this. Scores plots sort of generally the same, but your Q and T squared plots wandering out of bounds. And if you get a new interferent, chances are it's going to make a bias in your prediction here. And you can see here this prediction error wandering off in time. If you get a registration shift in your instrument, then it might look a little more like this. You'll still get Q and T squared with your new samples out of bounds. That probably will result in a offset between your predicted and actual values. That maybe looks like this. But determining the cause of the problem, I mean, that's a lot harder than just determining there is a problem. Might not be obvious from the model diagnostics. The measurement by the reference method is helpful. I would actually say it's beyond helpful. It's like, duh, it's helpful. Standard samples can pin down the cause unambiguously. And then what? Well, you have to expand your calibration set or do a slope and bias correction or some sort of instrument standardization. So adding samples to the calibration set is fairly straightforward. You just get new calibration samples in there. Sometimes it might take more than a few samples to add to a calibration set to effectively expand it into the new regime you're operating in. One solution to that can be upweighting of new samples, and there's several options available for doing that. Another thing that you can do is slope and bias correction. There is some physical basis for doing this. There's a reference below. It's simple to do. It might be appropriate for a constant shift. What we don't like to see people do is making continuous adjustments, like, daily based on a bias correction. That potentially indicates a problem is a variable interference or something else, potentially indicates an issue with your reference measurements. Could be that too. But that is something that you can do if your shift hasn't been too serious. And then, of course, there are the standardization methods. And there's a lot of methods available to estimate the response of your standard instrument from a different or changed instrument. And our favorites are direct standardization, piecewise direct, subspace standardization transformed, using GLS type filters or OSC. We've had good luck with all of these methods depending on the situation. Transfer samples. Most standardization methods require a set of samples be measured on each instrument so that they're paired. These can be chosen in a number of ways, and I don't want to get into that right now. But there are some methods out there that do not require transfer sets, and I've read the publications. We just haven't had very good luck with them. And so you can try those too, but I'm not going to discuss those at this point. Piecewise direct standardization, the basic idea is that you're going to try to use a window of channels in your secondary instrument to predict what the response would be in a single channel in your standard instrument, and then move this window down a channel. And so you get a model that relates windows in your instrument that you want to standardize to what the response would have been at a particular channel in your standard instrument. There's also the spectral space transformation method, which is a CPACT thing. We've had good luck with that. It develops a mapping from one spectral space to another based on common factors. And I won't go through the math on that right now. And we've also had good luck with generalized least squares weighting for standardization. The general idea here is to find dimensions in your data where the instrument responses are different and then shrink them in both instruments using generalized least squares or EPO filters. One nice thing is that the GLSW filter is tunable. You can really shift how aggressive it is, essentially. But if things are working well, your actual versus predicted analyte concentration might look like this for a near infrared data set. And if you apply that though to a changed instrument or a different instrument, you might get results that look like that instead. This is from that data set that was collected for CPAC by Amico, Ernie Bachman, way back in the 1980s, early 90s, something like that. And this was how well instruments typically matched for applications like this back then. They're better now, but there's still a shift. If you do some standardization, you can bring those predictions back closer to the line. Also, we've done a bit of work on model-centric calibration transfer, where you have a model and pre-processing step 1, 2, and 3. And so this last one is typically a mean centering, but you might be using a normalization and a derivative in here, something like that. And then your model. And now here is your instrument with your new data, and that might not work anymore. So what you might do is now insert a standardization step in between pre-processing steps. And that might actually be more effective, because here, this pre-processing step might get rid of a general effect like baseline offset or scatter. And that's so variable from sample to sample that if you get rid of that first, then doing the standardization on the data set with that removed is easier to do. So it might make sense to put the standardization somewhere in the line of pre-processing steps. Putting the pieces together, well, you need a method to identify the need for action, a method to update them, and tools for developing these standardization calibration transforms. So here's the roadmap. You start with your preliminary study and calibrations. You develop a maintenance plan. You put your model and instruments online. Bob discussed that. So is your performance okay? Yes or no? If yes, well, then you just keep operating. No, well, then what? Well, what's the source of the problem? Is it out of range samples, a new interferent, a change in relationships because of instrument or sample matrix? So if it's just out of range, then you can measure additional samples, create a new calibration model, and get that back online. If it's a new interferent, well, is it constant or variable? If it's variable, then you're back to measuring additional samples, creating a new model. If it's constant, you have the possibility of adding a slope and bias correction. Okay, what about a relationship change? Well, is it the instrument or the sample? If it's the sample, is it compatible with the old data or not? If things have really shifted, it might not be compatible, but if it's just a new variation that you can blend in with old variations, then you're back to measuring additional samples and creating a new calibration model. If it's not compatible with old data, then you're at the measure a whole new calibration set phase here, and then you have to create a new calibration model. And Okay, what if it's the instrument? Well, recalibrate it or standardize. If you want to just totally recalibrate, you can go back through the bottom line here and you're back at the measure the new calibration set and then get that online. If you can standardize it, then you have to choose a standardization method. And those behave a little bit differently. If you use GLS and OSC, then you actually do have to develop a standardization transform on the original data, develop new models and put those online, but you can use new models based on the old data. Or if it's you want to use direct standardization, piecewise direct, SST, develop that standardization and then get that in the chain of things and get that standardization in the model. Okay, so that's the roadmap, depending with all the things that I could at least think of on a plane ride, what might happen. Before I go, I just want to say a word about avoiding model maintenance. Some models are more robust to new analytes and changes in the data than others. That's highly dependent on the pre-processing options and the number of factors in your models. And we put tools in our software a long time ago to test model robustness to new interferences and registration shifts. Basically, these are a series of functions that test the model against these changes. So one of them that we use is the new analyte challenge. And we take a narrow peak and move that across the spectrum or progressively wider ones and see how that affects prediction error. And using an example corn data set that you've probably seen before, here's what you get if you challenge this model with these perturbations. And so here's narrow width to wide width, moving across the wavelength. So what do you see here is that the error goes up the most if you have a narrow feature in this range and it's not as sensitive to wider features. And we've kept actually the area under the curve constant here for the feature. An interesting thing is if you look at what happens with a range of latent variables here going 4 to 8, you see that even though this 4 latent variable model is never quite as good, it's never as dark blue in here, it's never as bad either when it gets challenged as by these new interferences, whereas models with more factors are less robust to that. And you can also look at it as a function of what pre-processing steps you've done. And I really want to point out the difference here is this is the mean-centered model. Here's a model with a first derivative. And derivatives, for instance, will really pick up on narrow features that get added to things. So they are somewhat less robust than models without that. And you can also look at it in terms of registration shifts. Here's the registration shift across the bottom versus the prediction error of the model. And 4 latent variable model is never as good, but it doesn't get degraded as fast. More latent variables, better models, but they degrade more quickly. And likewise with different pretreatment options. So here, this is your second derivative model is the one that is the most sensitive to registration shift, whereas this one with a generalized least squares really isn't affecting that much at all. So that's one more thing to look at when you put a model online is, can you get one that is less sensitive to changes in the data? Okay, so conclusions. Plan and budget for model maintenance. There's a lot of elements there: performance monitoring, problem identification, standardization protocols, remodeling and revalidating. I think the roadmap can be customized to specific applications, and model robustness testing can help minimize the need for model updating. I'll point out a couple of resources here for deployment and maintenance. Bob is going to be doing a class at Eigenvector University in Seattle this spring on model deployment and solo scripting. I think he kind of mentioned scripting in his talk. And we have a calibration model maintenance course that's in our recorded courses. And also in our recorded webinars on our website, we have one, Everything You Need to Know About How to Build and Deploy Instrument Standardization Models, is in our free webinars section of our website with an addendum about model-centric calibration transfers. And also this poster on calibration transfer by generalized least squares. And with that, I'd be happy to take questions.
Okay, thank you very much, Bob and Barry. If anyone has any questions, please type them in the chat box and make them visible to everyone. I can see we've got a couple at the moment. Barry, I think this one's for you from Brendan Lyons. What is meant by relationship change on the model maintenance roadmap?
Yeah, okay, there's one, you can get a relationship change between a sample and its response because the instrument changed. So that can change it. There's also things that can change it, like if you get a like change in pH or a pressure change or a temperature change that affects how your sample appears when you measure it, or sometimes, some other kind of matrix change. So that's what I mean, the relationship change between a sample and the measurement that you get.
Okay, thank you. We've got a question from David Lovett. Do you often use soft sensors to act as a backup to the measurement from the analytical instrument? For example, for powder moisture, what happens if the signal drifts or fails the monitoring test during a production run?
Well, I think soft sensors are a great idea. Anything that you have to check it against, I think is a good idea.
Yeah, I think there's been some quite nice work. I think colleagues from Pfizer, they gave a webinar a little while ago, CPAC webinar a while ago, I think, where they had a soft sensor running alongside near infrared measurements. And then we've got I think is it Thais? Apologies from Mondelez. Basically just saying thank you for sharing all of this knowledge. It was an excellent session. So that's to both Bob and Barry. So thank you.
Well, we're glad at least somebody liked it. So
it was brilliant. No, thank you. I enjoyed it. Yeah, and I'm sure lots of other people did as well. If there's any last questions,